Hello everyone and welcome back to day 4 of Advent of Code. Today's problem is called printing department and it goes like this. You ride the escalator down to the printing department. They're clearly getting ready for Christmas. They have lots of large rolls of paper everywhere, and there's even a massive printer in the corner to handle the really big print jobs. Decorating here will be easy. They can make their own decorations. What you really need is a way to get further into the North Pole base while the elevators are offline. Actually, maybe we can help with that. One of the elves replies when you ask for help. We are pretty sure there's cafeteria on the other side of the back wall. If we could break through the wall, you'd be able to keep moving. It's too bad all of our forklifts are so busy moving those big rolls of paper around. If you can optimize the work the forklifts are doing, maybe they would have time to spare to break through the wall. The rolls of paper, marked with at, are arranged on a large grid. The elves even have a helpful diagram, your puzzle input, indicating where everything is located. Here we have an example of how the warehouse would look like and where are our rolls placed. The forklifts can only access a roll of paper if there are fewer than 4 rolls of paper in the 8 adjacent positions. If you can figure out which rolls of paper the forklift can access, they'll spend less time looking and more time breaking down the wall to the cafeteria. In this example, there are 13 rolls of paper that can be accessed by a forklift marked with X. So here we can see, for example, that this roll, this one, is can be moved because it has exactly less than 4 adjacent rows. So it has 1, 2, 3, and we see that this adjacent tile is empty and this adjacent tile is empty too. Consider your complete diagram of the paper roll locations. How many rolls of paper can be accessed by forklift? So this is a very simple grid problem. I thought honestly it would be more difficult, but we are still on a part 1, so we can always get surprised. But what we literally have to do is traverse through our grid, row by row, and then column by column, and then just check if all of our if the current row and its 8 neighbors, or so-called adjacent tiles, contain any other rows, and if the count of those rows around it is bigger or equal to 4, then we cannot move it, otherwise we can. Now, first of all, we need to know how to move around the grid in coding. So let's say we have a position of this red dot, and we can give that position of, I don't know, let's say 2, 5. So it is in row 2, column 5. That's the position of this red dot. Now, how do we move around the grid? Basically to check, well, not move, but to check all of the adjacent tiles. This is extremely simple because all we have to do is, if we can see, adjacent means neighboring, so it's always off by 1 or by 0, depending on where we want to move. So for example, if you want to move here to the upper one, let me just change the color of this, we would need to decrease our row by 1, by -1, and keep our column as it is. So what does this do? Basically what we will need to do is come here, get our current location, and apply this value, and once we have that, we can just come down here, and then we will have 1, 5. And this number would equal to that one. So now let's do the lower one. The one below would literally be 1, 0, and basically the same logic applies. It would be row 3 and the column 5. Let's now move to the left. If you want to move to the left, now all we have to do is update our column, but keep our row intact. So what we have to do, I have a small dot here, which I don't want to have. All we have to do now is literally keep the row and decrease our column, and in this case our result here would now then be 2 comma 4. The right side is basically the same. We just remove the minus and that's it. All that is now left to do is to get the diagonals. And diagonals are literally you can look at it this way. If we would add the top and left, we can get a top left. So the solution to that one would literally be -1, -1. For this one, it would be -1, 1. For the top right, I mean. For this one, for the bottom right, it would be 1, 1. And for this one, it would be -1, minus, oh, sorry, not -1, 1, -1. And all of these green adjacent values, well, they're, how can we call them? They're offsets, or maybe even deltas, but I think I prefer offsets. These are the offsets of this position that marks the adjacent tiles in the grid. So now let's start writing our code, and what a better way than to start defining our adjacent directions that we will be checking inside our code. We can, inside our task, we can create a new variable called adjacent directions, and this will be a list of all of our adjacent directions, and it has to be a list because we want to iterate through them to check all of the values, to check all of the neighboring values. So we will start by doing 0, 1, oops, and then we will start by doing 0, -1, then we will start by doing 0, oops, 1, 0, -1, 0. Now all that is left are diagonals. Oops, I did something. I have no idea how. Okay, that just happened. Now we do 1, 1, -1, -1, 1, -1, and -1, 1. And now we have all of our adjacent directions, and there should be exactly 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Once we have that, we can slowly start going to write our main logic. And first what we need to do is basically get our grid from a file, just we have been doing with all of our other previous days. So we'll just get input.txt, not input, but the example input as f. Now what I will do, I will define a variable called warehouse, and I will first read all of the lines inside of it. And we can do that by doing f.split lines. Is it? No, that isn't like that. My bad. What I want to basically do is get this grid in lines. So it would be something like, if we would have, this would be like a first row, this will be like a second row, this will be like a third row, etc., etc. And then what I want to also do, while I have that, I want to also split each specific line so I can get each specific character in its own place. So how that would look like? We will use something in a Python, something that is called a list comprehension, and it is a nice way of writing one-liner for loops. We will our warehouse will be a array of elements. So what we will do is we will do a line.strip because we want to strip all of the unnecessary characters like new line character for line in F. And all that is left to do, since we have a string, to get all individual characters as an array, we just do list of line.strip, and that's basically it. If I would now print a warehouse variable and open a REPL, we can see now that we have a so-called 2D array where its values are basically our individual quote-unquote characters, or in this house, empty tiles and tiles with rolls of paper. Next up, as always, we need to get a collective sum of all the, well, not collective sum, we need to get how many rolls are available for us, how many rolls we can move. So I will just define rolls part1 equals 0. Now we can start writing our function, and I just want to immediately add this logic, so I don't have to worry about it later. So let's start by creating our function called part1. It accepts a warehouse. So what is our next thing? Now we need to get all possible movable positions. Why is that? Well, we want to know how many of the positions in the warehouse are actually how many positions are there where there is a role that can be moved. This isn't difficult, because all we have to literally do now is go through our warehouse grid to the array, and then just apply adjacent directions on the current value in the grid, on the current tile in our grid, and then just check if there were 4 or more rolls around it or not. My bad, less than 4 rolls around it. For that, I might define a function called def get total movable positions. So we can just have a function that will also hold the total movable positions. For this, I will be using a set data structure. Positions. I'll be using a set data structure. And why is that? Because set allows me to have unique values. There are no duplicates. And literally because of that, I want to get rid of any possible duplicates that might appear inside of it. That might appear if we would be updating our collection, in this case total movable positions, while we are traversing a warehouse. All now that is left to do for this function is we will define two for loops, because it's a 2D array, so one needs to be for our row and one needs to be for our column. For row in range, length of warehouse, because now we will get how many rows are actually in our grid, and now we will just do for call in range, for column in range length of warehouse on position row. This doesn't necessarily have to be a row, since we know our grid is basically a valid matrix. Since this row has equal amount of columns, this row has equal amount of columns, and this one too, and so on and so on. But I like to, instead of writing a 0 here, I like to define here a row, because then if at any case, for any situation, this has a variable, how do you call it, my god, different length, then we can just traverse it. So now we need to, now we can create our function that will basically hold the whole logic, that will be checking if if it is valid, if everything is valid. So we can do that by creating a function. I will create a function called movable roles positions. Movable roles positions. And this will accept a warehouse that we are currently in, of course, a row and a column. Now we want to keep, first off, we will define a variable that is called a count, and this will hold how many rolls of paper are around the current roll of paper that we are checking. We will also define two variables called max row, which is going to be equal to the warehouse, and a max column, which is going to be equal to the warehouse max at max row. Yeah. Why are we defining max row and max col? So what are we doing here now is we need to also keep in mind that there exists in Python, we can get an error called list index out of range. So how that happens is basically if we are in a top left corner, so in position 0, 0, and we apply -1, we are on this, for example, adjacent direction, then our row will basically be -1, 0 that we need to check, and -1 in a grid doesn't exist. There is a starting position of 0, 0, but -1 is somewhere here, which doesn't exist, so we need to create some sort of a boundary check. And there is a simple maths formula behind it. So we pass it a current row, current column, and then a max row and a max column. For the current row and not max row. So what we basically need to be checking is if our current row is equal or larger than 0, but if it is less than a max row, because our max row is a length of this warehouse and this length is always +1, so that's why we don't put equals here. Of course, we could put equals here if we would put -1, but for simplicity's sakes, we will just define this as less. And if the same thing applies for the column less than max col. And that's literally it. That's how we check. Now, to actually start checking the adjacent positions, we will create a for loop, which will contain a variable direction in adjacent directions, and then we will get a new row that will equal to the current row plus the direction at position 1, which will get this one, and at position 1 is our row offset, and for a new column we will have col plus direction of 1. Once we have that, we can start creating some sort of optimizations. We basically don't want to check or save checks or optimizations. So if our check boundary doesn't pass, new row, new col, and max row and max col. So if this boundary check doesn't pass, we can freely continue because we know the current direction, the current offset that we are using to check is not valid. And then we can also, then the last check we can also do is we can check if the tile in our warehouse at the new row that we defined, the new col, is equal to the paper roll. We will just update the count, and that's basically it. And now we can just return the count. Now we have these total movable positions. Yes, I think that's it. We define that, and now we can get here. I just now noticed that this naming doesn't make sense, so I will just get rename this to get count of adjacent rows. Get count of adjacent rows, and now we can actually define our variable in a variable function that will get all possible, that will return if the current position has a movable role. Get movable role position, and this accepts a warehouse, a current row, and a current column. So now we have if our warehouse, and we can also do a initial check here, so we can break out of the function early. If our current row, if our current tile isn't equal to the @ symbol, we can freely continue. Looking at this, we actually don't need this. Oh yeah, we do. Okay, never mind. I just thought there was a simple optimization that we can make, but no, because this depends on a new row that we have defined here. We can just continue, not continue, but we can return a empty set. Now we can get a count of our count of adjacent rows. Rows equals get count of adjacent rows. We pass in a warehouse, current row, and current column. If our count of adjacent rows is less than 4, we can return our current position. The curly braces in Python in this way define a set. So that's why I'm doing it. And we will return a set with a tuple that will contain current row and current column. Otherwise, our fallback will be to return an empty set. And what we will just do here, we will do total movable positions, and we will update our set with the get movable role position, warehouse, row, call. And that should basically be it. We just need to return now total movable positions. And we can now call movable positions equals get movable role positions. No, not the get total. And we pass in a warehouse. And we can just return a length of those movable positions. So now let's check if that will work. Part 1, we do roles part 1. And we get 13, and that is the correct answer for the example. And let's just check if we will get a correct solution for my input. 1433. 1433, which is a correct solution. Now we can immediately start with a part 2. Part 2 goes the following. Now the elves just need help accessing as much of the paper as they can. Once a roll of paper can be accessed by a forklift, it can be removed. Once a roll of paper is removed, the forklifts might be able to access more rolls of paper, which they might also be able to remove. How many total rolls of paper could the elves remove if they keep repeating this process? Starting with the same example as above, here is one way you could remove as many rolls of paper as possible using highlighted @ to indicate that a roll of paper is about to be removed, and using X to indicate that a roll of paper was just removed. So this one was a bit of a mouthful, quote unquote, to say when I first read it, but it basically goes like this. We get the initial state, of course, our example, and then for all of those 13 rows that we initially had, we remove them. Then we will have a second state, or or how the warehouse will look after we remove those 13 rows, and then we apply the same operation. Then we will get a state, some new state. Then we do basically the same, and same until we are left with a warehouse arrangement of rows where we literally cannot remove any more rows. So step 1, no more rolls of paper are accessible by forklift. In this example, a total of 43 rolls of paper can be removed during all of these stages. Start with your original diagram. How many rolls of paper in total can be removed by the elves and their forklifts? Now this part 2 really surprised me because I was immediately waiting, as we might see in the future days of Advent of Code of this year. I was immediately waiting for some pathfinding or something, but this turned out to be extremely simple because all we have to do is basically keep looping through our warehouse until we know we cannot remove anything. And this can be done in so many ways, and I have seen a lot of people brute force this. For example, when I was just solving this at my work, first time I literally just decided to run the code for 1,000 iterations, and then I got a number and it literally worked. But of course we won't do that because that's extremely inefficient. There is a smarter way to do that though, and it requires us checking these movable positions. So let's get to writing our part 2. We will first, of course, define a part 2 roles part 2 plus equals a part 2. And we will pass in a warehouse, of course. So now let's get started. We will create a part 2 function. Oops, I don't know how to write, that's my bad. Okay, first of all, I will do this in a recursive way. Of course, there is a way where you can do it literally using a while loop, which is totally fine. And that's how I did it first time, but I don't know. To me, a recursive function is pretty much cleaner. But that's literally on a subjective opinion, because some people might say recursive way is unreadable, not in a way that it looks uglier, but because it's not easier to understand cognitively. We will first get all of our movable positions. Movable positions, we get total movable positions by passing a warehouse. So each recursive function needs to have a breaking point. And this is where I said that instead of me running 1,000 iterations like I used to do, like I did first time, we will just check if these movable positions is empty. And why is that? Because that would mean the get total movable positions function will literally return us if what positions allow us to have movable roles. If it returns nothing, that would mean, hey, there are no movable roles available for us. I will just put this back to example quickly. And so we will do that. If length of movable positions equals to 0, we just return a 0. So that means the number of roles is just gonna be that, and this return will just say stop there. That's literally it. If mobile positions isn't empty, what we need to do is update our warehouse state with all of those positions that can be moved, and we will replace them, and we will replace those positions in a warehouse with a dot. So we just do for position in a movable positions and a warehouse of position at 0 and at position of 1. We are doing this because at position 0 we have our row index, and at position 1 we have our column index, and we'll just replace it with a dot. So all now that is left to do is call our movable positions, the length, plus again calling this function recursively by passing it a new warehouse state. And that's it. That's the whole part 2. I was a bit shocked at first too, but it works and it's simple. It's honestly refreshing to see something like that. So if you run this code, 43 is the correct example answer. And if we would now change this input example to my code, we would see that I get 8616, which is the correct answer on Advent of Code. Now, just as a bonus, I just want to showcase an animation that basically shows how the part 2 works. So right now I set it to update every 0.3 milliseconds, just so we can get a general gist of how things are working. As you can see, it's nothing too crazy, but it's always sometimes nice to visualize your data like this. Number 1, because it's fun. Number 2, because you might learn something. And now to just showcase a faster version. And that's it. I hope you guys have enjoyed this video, and I hope you guys have also learned something. Until tomorrow, have a nice day, and peace.